recording. Okay, so during the last lecture we have been looking into flow control, and we looked into ifs and switches, which are already quite useful, and in the way they operate in a sense similar. They allow to take different branches in the code depending on what if some condition is fulfilled or not. But what we haven't looked into yet is the ability to process something multiple times, basically loops, so that we can repeat the same part of code multiple times until some condition tells us that we are done. This is a very useful and very basic capability of any programming language, and of course C++ offers quite a few such mechanisms as well. So let's start with the most common one. It's a for loop. It starts with the keyword for, and then you can specify 3 different things which will happen in different stages of the execution of the loop. The first will be executed only once when the loop initializes. So here we can, for example, define a variable like an integer, which will be, for example, incremented each time we go through the loop. I guess it's quite apparent that the simplest type of loop would be one which has a counter and is counting up or down until it either reaches 0 or a selected value and then stops doing. The loops can of course be substantially more complex, but the simplest and also a very common type are such loops. So first we initialize our loop variable, then we have the condition. So let's say I is less than 10. So the loop will repeat itself as long as I is less than the number 10. And then the last thing we have a small piece of code which will be executed once the body of the loop has finished. So for example, here we can use I++ to increment our I variable. And then of course we have the loop body. The loop body can either be a code block with curly brackets, or it could be just a single line that does something. So of course a full code block is more interesting, so let's go with that. Let's define some other helper variable, int my counter, and the simplest thing of course would be to just count a counter up, or we could something more interesting. My value is, let's say, what would be interesting. Well, let's just start with, we can even start with 0. So no, this will not be interesting. Let's start with 2, and then we could, for example, say that value is equals value times itself. So we just multiply itself with itself, and this is our next value for the next iteration. For something might be useful. So since we already have it, so let's take a look how this behaves. We will put a breakpoint at the start, and then we can investigate how the generated code looks like. And I think we might want to turn a few things off to simplify it. Code generation, no. Basic random checks, no. And what was the next thing? All options. This we don't want either. No. Let's see if this helped a bit. It's still just as complicated. Right, we are in the wrong breakpoint. Okay. So we start with something very simple. We just write 0 into some designated memory area, So it's basically this code. Then we have a jump. We jump to the condition. So the loop will test even before the first execution. At least this type of loop will do it, whether the condition is fulfilled or not. So then we have here our compare. Then we have a jump if greater or equal, which it is not. So we just continue. Here inside we have of course our loop body, which just multiplies the numbers and writes them back. And then we have a jump back to this place. And here what we are doing is we load our I variable, we increment, then we save it back, and then we automatically then continue execution down to the condition, which then, and the whole thing basically repeats. At some point this will not longer be true, and then if we put a breakpoint here, we run it, we will reach this breakpoint. So yeah, that's that. That should not be 0. We started with 2. That's weird. Breakpoint, run. Right, so we start with 2. So apparently we have reached a too high value, so let's go with int 64. No, that still didn't work. Let's see what happens. So look on our locals, what we have. So we have 2, 4, and then we are too far out. Yeah, it's just grows too much. Let's just make something simpler. Value plus equals value times 2 or something like that. That will be always 0 as well. Let's start at 1. Then we can use normal int. Zack. Okay, now we see that it actually did something. And of course, if we have created a loop, we might wonder if there are some ways to manipulate the way this loop will behave. So obviously one thing we could do is just write something to I. So for example, we could say if it's greater 100, then I is equals 10. This will then basically break out of the loop early, because our I variable is changed, and then this condition is no longer true, and then it finishes. Of course, this is quite an unelegant way of doing so, although there might be cases where this actually is a workable option. The typical behavior here is to use the break keyword. So it's a break like in our switch, just that this break breaks out of the loop. One limitation, for example, is that break only breaks out of one loop. So if you would have a loop inside another loop, then with a break statement you could not break out of the outer loop. And this, for example, would be a case where actually manipulating the loop variable or an additional helper variable. So for example, we could have a boolean, which basically just a char or an int to break, and then we just say for this and not to break. So these are different ways to achieve the same goal. To break is true. Alright, and here we should write false. Same as 0, but looks nicer if we use the right keyword. And now, of course, the behavior will be also the same, that we just end the execution of the loop, but you already see that you here can in fact specify quite a complex equation. You could, for example, also do the incrementation here instantly, not here. So there are many things that can be done with such a for loop. It is quite flexible. So of course the next question one might pose is, are there other ways to modify to manipulate such a loop? So for example, let's make a breakpoint here first. So we see our first value is 3, our second value is 9, our third value is 27. So let's go with 27. If our value is equals 27, then let's put it here so it's more useful. Right, so if it's 27, then we could, for example, want to not execute the rest of the loop. That is something quite obviously useful. So you just want to just jump to the next entry. So for example, if you would have a list of files and then you would want to process them, you could have at the beginning of your loop something that checks the file name, and if some condition is met or some condition is not met, then the rest would of course be skipped. So this can be done with the continue keyword. Oops. And basically what continue does is it instructs the loop to just directly skip to the increment section of the code and then execute here the comparison and then see what it is supposed to do next. Of course, one could also do something like this. Then you don't need the continue. That would functionally be equivalent, but the usage of the continue keyword might be in certain scenarios more elegant. For example, if you would have like multiple conditions which you want to check one by one, you don't need to create like a very long if with a lot of entries. You could just create a couple individual ifs, or if you would want to still create individual ifs but not to continue, what you would then need to do is like you'd have an if and an if, and each time your final body would get indented further and further away, which also is not great for the readability. So having the ability to just have multiple continue statements makes the code quite a bit more readable. So let's put a few breakpoints here and there and look how this is implemented. And of course it's quite trivial. It is just a jump to a location. So if we follow this, we just jump here to our increment code section, which then continues to our comparison, and then of course everything continues as expected. Oh right, and we of course already implemented a bug, because if this is of course true, then at this point we'll always just continue and never go to the next value. So let's say plus equals 10 or something, so that we just go past the case. So if we now have this fix, we can then reach our break statement, which again is just a jump out of the loop. So it's on the machine code side, it is quite convenient and quite trivial. So it works very fast, and as said, you can of course have inside the loop another loop, so there is really no limit in that sense. But before we take a look on that, let's improve maybe our sample a slightly bit. So let's say our counter, let's make it do something interesting, starts with multiplying. Then we have here our continue, so we need of course to set a value to this. Let's maybe go with 12. Oops. 12 and then here let's not do this. Let's then instead have another check. So if counter is greater 10, then we want to break. And in addition, we could also add maybe a counter. Let's do it differently. As long as this is below 12, below 12, we just continue. So first the loop will do a few runs here, then it will start doing this code, and then let's add here something to do. We will switch to just also making it plus plus, incrementing it by 1. Or let's write plus equals 1. Yeah. Okay, so more or less this much to this for loops. One thing to know is that in principle you can define a few more variables with comma. So this works, although you cannot define it with a different type, so we are a bit restricted what you can do, but as long as you stick to the same type, then you could do it. And of course you could also here comma separate a couple of more instructions which would do something, but generally you try to keep those areas as simple as possible, maybe with a little bit more complex condition, but don't try to make it too complicated, because that again is not great for the readability of the code. And of course, as we remember, C++ doesn't care for line breaks, so we can write our loop like this. I haven't seen anyone actually doing it, so it's not really a convention anywhere, but if you like, you can. Okay. So let's see what other loops we can implement. So the next type of a loop that is although before we do that, yeah. So the next type of loop that you can implement, well, that you can use in C++ or C, is a while loop, which is quite simple. It just takes a condition and nothing more. So let's reset our value to 1, and we just write while is greater than or is less than 10, and then you have a code block that does something. So in principle, this is quite exactly equivalent to a for loop, just written like this. But of course, this looks a bit nicer, so it has been provided, since often if you would have some external variable and then something happens, then you would not want to always use a for loop with not everything, with not all of its features used. And then of course we can do something inside. So in this case we can, let's say we just increment it. We can of course put a breakpoint to see how it works. It will be very similar to our for loop, just with a little bit less code. So we just have here a comparison, a jump, and then at the end, of course, a jump to repeat the loop, unless we have broken out or something like that. Inside the while loop, you can use the same types of keywords, so you can break or continue as you desire. So this is quite nice. And there is yet another type of loop that sometimes is useful. It's a do while loop, and what makes this loop special is that while those two loops always check the condition, the do while loop only checks the condition at the very end. So let's add some comments. For loop while and do while. So here let's add something. Right. So as said, such a do while loop behaves different, as it will always execute its body at least once. So when we start here, we have our assignment 1, so it's actually not part of our loop. Inside loop we have the loop body, in this case just incrementation, and then we have our comparison and the jump, and then the thing repeats until the condition is met, and then it continues going down. Such a loop, as also the others, might be also useful in special cases where you actually don't really want to repeat something. So what you can, for example, do is you could create a do 0, and then have in your code some if greater 10, then break, else or something like that. So the usefulness of this is maybe not instantly apparent, but in fact it is quite useful, since in C and C++ you usually need to manage the lifetime of your objects. So unlike more higher level languages where object lifetime is more implicit, in C++ you usually have to manage it explicitly or use special mechanisms to make it automatic, but that these are more new. So old C and C++ code does everything by hand, and there it means that usually in a function or at the end of a function rather, you would have some section which cleans up all the resources which you have allocated. And such a do while is quite nice, because you can have a very complex code block, and at any point in time, if an error happens, you can just break out of it, and then after the code block have your cleanup section where you then free or the resources that you have allocated. Yeah. Any questions so far? Okay, so if there are no questions, then let's continue. So we have taken a look on the types of loops that one can use, but so now it will be time to take a loop on putting loops inside other loops. So and this is also something that usually is quite useful. So let's just start with a for loop again. For and e is equal 0, e is less than let's say 3. Then we will also add our break mechanism, and it's not break, and I plus plus suck, and inside we can just make another loop. Just we should of course change something, otherwise it will be quite boring. So let's do it like this, and now let's also reset our counter variable, and here let's this time okay, let's like always start with 1, and here just as a function I just increment this by 1. So the result should be like 10-ish, because we already have a 1 inside our counter. So let's put a breakpoint here, and as once we arrive at our target breakpoint, we see that this basically is just a loop inside a loop, so it looks identical to a single loop, just that there are two cascaded. The code is not really changed in any significant way. And of course, we can just step through it. First, of course, the inner loop gets executed a few times, and then the outer loop. And then, of course, once we are done, at some point we will stop the execution, and we will have our expected value in our variable. You can, of course, inside this loop access both e and I and j. So that is something that I probably should have mentioned earlier. As soon as we had our ifs, you can define new variables inside every code block, and you can use them, and the lifetime of those variables will be restricted to the code block. So we could, for example, here define some int x, and here we cannot access x anymore, but here inside we of course can. So this is quite useful, since in very old C code it was kind of customary to define all your variables at the very beginning of a function, so not really in the context of what the variables necessarily have been used to, which might appear a bit inconvenient, especially if you have very long functions and you would need to scroll to the top to add a new variable. But since but in modern C you are not doing this, you can first of all you can define variables anywhere, as we did here, for example, like this, and they just will exist until the code block ends. The compiler internally might still sort when it's optimizing the variable initializations to the begin, but this is not something that is for us of a large relevance. And as already mentioned, we can use so as already mentioned, in such cascaded loops, if we want to break out of them, we need to be a bit more creative how we do that, and this such a break variable is one of the more convenient approaches of doing this. But there are also other ways. So let's just try a few other options. So one, of course, would be to do it in a way a bit more manually. So let's say here I will just don't want to do anything breakthrough. Yes, do here the same. But then, of course, let's add a condition. So this is not too boring. So if this is greater 5, then we want to break. Yeah. This will keep our loop not completely pointless. Of course, we break, but now we only break out of the inner loop. The outer loop would still be repeated, which actually would be, in a way, in this particular case, actually not the worst thing, because we would then just check again, break out of this loop early, and we would arrive at the same final value. But obviously one should notice instantly that such an approach would be quite inefficient, because we would still loop through a lot of code which then basically does nothing. So what we would want to do in such a case would be to set our break variable. And then of course we could either have the variable here, or we could have an if break break. And of course in this case we could also just check with this if. But this is, for example, bad practice, because if you have very large code, a very long function, very long loop, and then you want to change 5 to 6, and then you forget changing this, then you will potentially end up in wondering why you never get the right value. Or in some cases you might have sometimes the right result and sometimes not, depending on what you are doing. Since here internally I guess we would always break out, and outside we would see values outside of the 5 range, since we are working in freeze. So what is recommended is to have a check and then a flag which represents the status of the check. So this could also be written like this. So do break like this. For making it look nice, you can put it in brackets, although it's completely unnecessary. And then have something like this. It is a bit more manual, and of course just putting the break variable here usually is preferred, but as said, with more complex loop structures, you might for some reason prefer such a more manual approach as we can use here. Next thing that should be mentioned when thinking about this flow control is a quite old mechanism which was present in the earliest programming languages, and something that in a certain way you have already seen here. You've seen this jump instructions in the assembler interpretation of our code, and in such a jump instruction basically does not implement some higher, more complex form of structure like an if or a for. It is just a instruction to the code, just go somewhere and continue execution from there. And this in fact can be done in C or C++ as well. There are some restrictions on it, but there are use cases where it is useful. And in fact, breaking out of loops is one of the use cases where it's not frowned upon to use such a mechanism. So let's do it. It is called a goto. So we have here our things, and then we say just goto. Then we need to provide the name of a label. So let's say goto loop end, and of course loop end. We need this to loop end, and of course we need to then install this label somewhere. So here it's, for example, complaining that the label was not defined, and the label can be defined anywhere, either above or below, basically anywhere inside your function. It will jump to there, and of course in our case, if we want to end the loop, then our label should be here. And labels you usually try to either have always at the very most left, basically not indented, or you would indent it. So if you would have like a larger code block, you could indent it to the parent code block at which level you operate. So this, of course, then we don't need this anymore. So such a goto can be used anywhere. You can, and you should usually have some condition, although you could of course add some unconditional goto somewhere as well. This will work just fine. So let's put a breakpoint here and see how this behaves. Again, we are in some different breakpoint, zack, and you see it is just implemented as a jump instruction to loop end. And for some weird reason, the compiler sometimes generates 2 of those instructions. I have seen this already before, and the second one is completely unnecessary. It will never be reached. Also, if you build a debug build, then a release build, then this will also be optimized the way it's only present in case of a debug build. One thing that you here may notice is that those values are actually not identical. Since one might think, since we are jumping to the same location, they should be, and they could be, but if they would be, then they would need to be such a hugely long number. Because then it would need to be a absolute address, and an absolute address is long. 64-bit system, it's 8 byte. Plus, working with absolute addresses is inconvenient because you don't always know where in memory your image will be loaded. So if you would rely on absolute addresses, once the operating system is loading your image, it would need to change all those references on the fly. Otherwise, they of course would be invalid. So what is done almost always is that the jump is relative. So it doesn't tell like EB is jump. It doesn't say jump to this. It just jump 0e bytes further down. And since these instructions are not at the same position, this one jumps by 2 bytes less, since it doesn't need to jump over itself, so to say. And this you will see in quite many places, that in such assembly code, that whenever possible, relative addressing is used instead of absolute addressing. It allows to save on code bytes, which actually is quite important because it does not only make the application binary itself smaller, but it also reduces the load on the memory bandwidth. So you, when you are programmed to execute, needs to load less stuff from RAM into the CPU all the time, then it will work more efficiently. Of course, the CPU nowadays has a lot of caching, so depending on the scenario, you might or might not really notice a large difference. But as soon as you would have code which is large enough such that it would not fit into the cache anymore, then such things are extremely critical. So if you would be programming some very high performance code piece, some, I don't know, pi number computation or something, then you would, if it really needs to be super fast, you would try to write it in a way that your entire code would fit into the CPU's cache, which of course, depending on which CPU you have, might be easier or more difficult, since CPUs have different amounts of cache, obviously. But if you can fit everything in the L2 cache, that would be probably the best performance you can realistically get. Fitting it into the L1 cache is probably unrealistic, unless it's a very simple loop. But generally, such mechanisms to reduce code size are quite beneficial. And of course, with modern compilers, this is not longer something in the most cases where the programmer has to care about themselves and put work into it. You just enable the right optimizations, and the compiler will generate for you quite optimized code, which in the general case will be good enough. In special cases, of course, manual optimization might be useful, and this optimization you can change in the project properties. And of course, in the debug build, it's disabled. But the typical optimization types are either for speed or for size. So you can usually not optimize both at the same time. And you also have some additional optimization options, like whole program optimization, that would look for redundancies and try to minimize redundant code across different object files. Usually this is not really worth it, in my opinion. So normally just optimize for speed. And usually this will also give you better speed even if the code is slightly bigger. So it doesn't mean that it will not do the other optimization. It's just what is the preference. It will still try to optimize both parameters, but when it needs to make a trade-off, this just indicates in favor of which it will do this trade-off. Okay, so let's see what else we can do with such a goto. So generally with such gotos you can implement loops yourself. So let's see for a simple case. So we could have a well, an infinite loop, for example. Infinite loop. label, go to infinite loop, and then our loop will never finish. So that's obviously something not quite great. And this is something that even when you are using normal for or while or do while loops, what could happen. So there are various scenarios where you might not break out of a loop. So for example, if you don't always use a loop variable which gets incremented with every iteration. For example, you might have something that waits for an event from some hardware that will just wait forever until this event comes, and if the hardware is broken, this event might never come. So that would be one scenario. Or when you want to receive data from the network, you would also run a loop that is waiting and reading data, and if nothing ever comes, the loop will be stuck forever. So it's quite common as a bug that the logic of a loop is not quite ideal, and then there are special cases where the loop maneuvers itself into a situation where it will then just keep executing forever and never break out. So if you expect in a certain scenario that such a thing might happen, it is good to just add some break condition to break out of the loop if some amount of iterations within some specified amount of iterations the loop does not finishes successfully. And then of course you should check this condition and return an error or something. So this is quite something to keep in mind, that it can happen. And there are also scenarios where you would want to really create an infinite loop only with a break condition. So for example, in case of our for loop, which the simplest way is for, and this has no condition, it will run forever. What you might also find in older code is something like while one. And the opinions about while one are a bit varied, because on one hand, if the compiler does not optimize really anything, while one will contain code which will always compare one to one and then continue. So it will be wasteful. But even in the debug build, I think modern compilers, if they see a while one, they just turn it into a really infinite loop and don't waste CPU cycles on checking something that really never will change. And of course, inside such a loop, you need some break condition, otherwise your application will be stuck. One example where you actually have a while loop which is supposed to never terminate is in most of Arduino sketches. So programs for microcontrollers usually start up, initialize some stuff, and then reach a loop in which they then loop forever until the device is reset or power cycled. They never exit the main loop. And in principle, you could if you have some simple console application, you could try to go for something similar, but obviously an application from which you cannot exit would not be quite nice. Although on Windows and as well on Linux and pretty much in most operating system that offers you some sort of terminal, if you press a special key combination, you can just kill whatever process is running right now, so you can exit such a infinite loop even if the program as such does not want to allow you to do that. So as I said, you can of course also write an infinite loop like this. So let's add here a condition: if is greater 10, then well, we need another loop end, and this is, for example, one reason why actual for and loop infinite loop end. While the normal loops are so nice because you don't need to invent new labels each time you want to create a new loop, because here like we need one label for the end, one label for the repeat, and so on. So it gets complicated quite fast. So I think at this point this is quite a nice idea for a homework. So homework from the 26 032026, and we'll just take a simple for loop. Now let's take this one. Um, Then let's create a multi-line comment. Homework from the into only ifs and go-tos. I think this is quite easy and not too complicated. Let's see. Let's not make it too difficult. Let's just do it like this. So I think this is quite a simple assignment. It just means to add a few loops and a few labels and go-tos and a few ifs. So it should be quite simple, and I think it is a nice exercise to really visualize oneself the code flow inside such a loop. So what is executed when, and yeah, and that's that. Any questions? Okay. So if there are no more questions, then let's continue to something new. So we will create a new project. Although maybe one more idea, we could also make the for loop maybe a bit more complicated. Nah, I think this is good enough. If it would be more complicated, it would be just Fleißarbeit. What's the English word for it? Busy work, which is not necessary. From a more complex loop, I don't think one would learn so much more. So let's keep this open so that I don't forget to upload it to Moodle and create a new project. Create new project, console application. Let's call it pointers. So if you remember the assignment about the conversion of a floating point number to its constituting elements, there was a code line where we have done something like this. Float my float 0.4, and then we had a int my int, and what we then wanted to do is wanted to get the content of the float into the int without actually doing the actual conversion. So not having 1 to 3 as a result, but really having the memory content of float inside our integer. And we done this somehow like this, and I didn't really explain what's happening. So now I just said that this will give you the memory of float into my int. We can also take a look on this here in the disassembly. So as we see, it is just a move operation. Take the memory at the position of my float, put it into Ajax, and then take the value from Ajax and put it into the memory at the position of my int. But how does this really happen? How does this work? So in C++, there is a concept of a so-called pointer, which basically is just a 32-bit or 64-bit or whatever the platform address bitness is, integer type variable, which so basically it's a number, but its semantic meaning is that it does not contain a value that you're actually interested in, well, not directly, but it contains the address in memory of something you are interested in. So let's see how this looks. So we just comment this out, and let's start. So let's start with something really simple. So let's just first define something that we have something in memory that we might be interested in. So my variable is equals 1 to 3, and then we will want to be able to somehow refer to this memory that contains this number. So um, in the an interesting thing is that while all the pointers are always the same size on a given platform, so if you have a 64-bit program, all the pointers will be 64-bit. If you have a 32-bit, then all the pointers will be 32-bit. But purely on the level of the programming language, as such, you can specify already a type for the pointer. So machine-wise, all pointers are just a void asterisk my PTR, and then you should initialize it to something. You can either use null, which just evaluates to 0, or a more modern way, something that so null is what you do in just C code. If you have C++ code, and a modern one at that, a more approved keyword is null PTR, which effectively is all those things just evaluate to 0, but it kind of makes the code look nicer and omits a preprocessor step with this null macro. By the way, what a preprocessor is, we will take a look a bit later. It's a mechanism that allows you to in some way simplify a few things in C, but it's not something that's so directly important when you are just trying to understand the very basics. So this is something for later. And if we have, coming back to our pointers, when we have such a pointer, we can just assign an address of something to this pointer. So we do this by using the AND operator and then providing a variable name. And what this does is it will take the address of my variable instead of its value and assign the address to my pointer. And we can put a breakpoint and run it so that we see what happens. And we see, okay, my variable is 7b, so it's 1, 2, 3 in things, and our pointer is some large number which is representative of the memory location. And we can use here one of these memory views to go there, and then we see it contains our 7b and then a few zeros. So it really is just an address. And what you then, of course, what one might want to do is to do something. The simplest way would be to read it. So let's say int my var2, and then we would somehow want to get the value from my pointer into our my var2. But as you see here, the direct assignment doesn't work, so it's complaining. We need somehow to get the value out. So we need to tell the compiler we don't want the value of the pointer, but we want the value the pointer points to. And usually when doing assignments, the compiler will not allow you to assign a pointer to a value, even though both are integers. So if this would be a int 64, they would be perfectly compatible memory wise, but of course semantically they are incompatible, and thus the compiler doesn't allow you to do it. Generally, when you have a pointer, to get to its value, use the asterisk operator, but the compiler does not track which types you have assigned. So if you have a void pointer, you can assign anything to it, but then you kind of cannot just take the value out because it's a memory address without the semantic of what is located at this address. So the most basic thing that you already don't know is how long is this memory range. So we, seeing the code or remembering that we assigned the address of my int, know that it's 4 byte, but the compiler doesn't track that, so it doesn't know, and it could be 1 byte, it could be 8 byte, it could be an arbitrary amount of bytes. So somehow this information need to be provided what it is, and one way of doing it is to cast it. So that we provide a pointer type int asterisk in this case, and then so we write the type and then asterisk, and then the pointer is of this type, and then as soon as the type information is present, we can dereference it, and then we will get 1, 2, 3 in here. And the other way to do it is to already define the pointer with a specific type, which is usually the way how you will work with pointers. So it is not necessarily a great idea to use void pointers everywhere and then casting them all the time. There are legitimate use cases. So if you really have just a large undefined amount of memory, for example, if you want to write something to a file, a function that writes data to a file will take a void pointer with some data, and then it will take a second variable, length or size, which will tell the function how many bytes actually they are that can be read from this memory address that it has obtained. But this is something for later. So in the normal case, you would want your pointers to have a type, and of course, as we have seen here, we can so basically reference at myFloat would give you a float asterisk, and then you can convert a float asterisk to an int asterisk, and then you can dereference it. So this is how this old code here, how this really worked under the hood. Everything clear so far, or are there any questions? Okay, so then let's take a bit more looks on our pointers. So the C language provides quite a nice keyword to obtain the size of a type. So here I told you that int is 4 or uint 64 is 8 byte and so on, but there are cases where you actually want to know this value inside of your code, and ideally you would not want to hard code it, but really in case you want to compile your code on different platforms, have this value be properly retrieved. So we can write an int, and then my size is equals size of, and then we can provide a variable, or we could also use size of type directly. We could also write size of int. So both are valid. And this gives us, it returns basically really the size. So we can also make my pointer ptr size, my ptr. And then when we run it, we'll get here at runtime 4, and for the other one 8. Since our integer is only 4 byte and our pointer is 8 byte, we get the right values here provided by our size of keyword. You can do, of course, a bit more exotic things as well. So, for example, you could, if you want to, if you have a pointer and you want to get the size of the base type, you could write asterisk ptr. Then both will be 4, for example. And as already mentioned, you could also just write the type in here. That would also work. And funnily enough, the size keyword also works without brackets. I think generally speaking, they just defined it like this, but people used to use functions always do it like this, and the C++ language is tolerant enough that it will just then drop the brackets, and you will get the same result no matter how you format this. Okay, so let's see. Let's get some more feelings for for our pointer types. So let's see, can we order this a bit more elegant? Yeah, let's do it like this. Oops, this here. Here we get the access. Right. And then we have a variable. So the next thing, of course, we might want is to somehow assign a value to something. But before we do this, let's define a second pointer. My pointer 2, and then let's assign the first pointer to the second pointer. Okay, so now we have a variable and 2 pointers which are pointing on. Then just for good measures, let's even define a third one. My pointer 3 is equals reference my variable. So we have at this point, when we run it, we will notice that all those 3 pointers, my pointer and my pointer 2, my pointer 3, despite they all started their existence differently, they all contain the exact same value. And now if we, for example, change the value of 1, 2, 3, since the pointers only point to memory, obvious 7b, that needs to be updated. So this view here just shows always the old data. Let's go to the locals. Yeah. So let's put the breakpoint here. Let's run it again. So we see they all contain the same values, and as soon as we change the variable, basically the memory that is pointed to, then we see all the pointers now of course point to a different value. This might sound obvious, but I think if someone really does not have any familiarity with the concept of a pointer, that might not necessarily be so obvious. So it's good to try such things. And of course, what we can also do is we can pick any of those pointers, dereference it, and then assign the value this way. So if we are assigning something to a dereference pointer, like here, what happens is that we are not assigning a value to the pointer, we are assigning a value to the memory the pointer points to. So click, and as we see, the pointers didn't change, but the value in memory they point to has changed. Okay. Everything clear so far? Yes, so there was a question in the chat whether the myPointer variable has an own address, and yes, it has. And we can get the memory address of this pointer, so we can just write int asterisk asterisk, that's a double pointer, basically a pointer to a pointer. My pointer to a my ptr to ptr, and then we can just assign it by dereferencing one of the pointers. Let's go with pointer 3. Okay. So if we run it without this, we see that the IDE here actually shows us like this pointer now containing the memory address of the other pointer. So this is the memory address of the other pointer, which then contains the previous value, which then contains the other value. So you can in fact cascade this as far as you wish, and you can then of course assign values like that. Or what you could also do, you could make the pointer point to something else. So let's do this. Let's create another my variable 2 with the values x. So we can have a pointer to a pointer. Well, that is a bit too complicated. Let's do it here. So we have our normal pointer, and if we just address it directly, then we can just change where the pointer points to, which is quite useful. So you can have you use pointers, and then with pointers you can make your code work on different memory blocks, and the only thing you need to change is the pointer that points to that memory block. So a pointer can be reassigned to point to different memory at any point in time. And in principle, as said, you can have also a pointer to a pointer to a pointer, but at some point that will be pointless. Because usually you should not try to make the code too complicated. If you would want like pointers to pointers to pointers, then probably there is some way how you can redesign your code to work simpler. So this is a pointer to a pointer, and then we change the pointer to a pointer, and then we can change the pointer we are pointing to point to. Wait, and that's already complicated. So we have assigned var2 to pointer 3. We have assigned the address of pointer 3 to my pointer to pointer. So we have effectively changed the content of variable 2. So now we want to change pointer 3, which points to variable 2, to point to variable 1. And then we want to change this value in, let's make like this. Okay, and then if we run it, then we will end up with we have a bug somewhere. Oh, I already used variable 2. I already used variable 2. Then let's call it variable 3, obviously. Right. Okay. And then we ended up, of course, let's disable hex display, changing this to 222 and changing this to 111. So by reassigning the pointer, we were able to change the behavior of our code, and in fact we not just reassign a pointer, we assigned through reassigning a pointer to a pointer. So we could also let's define another variable, or let's use this variable here. Do we have a pointer that points to variable 2? We don't. So let's make another pointer. I'm using all of them. We are using pointer 2, we are using pointer 3. We are using just pointer. Yeah, okay, so let's here maybe reassign pointer to point to our variable 2. And then so we have a pointer to a pointer. This points to my and this initially pointed to pointer 3. Pointer to a pointer. We do not really have my pointer 3, so let's now assign just a pointer to a pointer to point to pointer this variable. Then again, if we write something there, it will end up there. So we will get 1 2 1 2 2 2 sorry 1 1 1 2 2 2, and here 3 3 3. And as you might already notice, such code if it's written like this without comments or anything, gets very very convoluted very quickly, because you need to then kind of track in your mind what is your current pointer to pointer pointing to right now. And it might, and this, as you have seen here, you can change easily at any time. So it is a very powerful mechanism, but at the same time it has a lot of potential to breaking something. So you should be careful, and ideally you would want to not reuse pointers too much, but just define new ones with descriptive names that tell you what they are doing and what they are for, and then keep them doing this thing instead of just reusing them in order to save a few bytes of memory. So if you look into some very old code, a very old C code, you would often find something that is just a variable which is just called pointer, often of type char or something similarly generic, and then it would have different purposes in different places of the function, which kind of saves you a few bytes of memory, but at the same time it makes the code quite unreadable. So let's continue. So this would just pointers, and the next thing which we should take a look are arrays. So as you know, the CPU can only handle defined known types which fit into registers, and this is quite limiting. So a mechanism in C and C++ which helps to alleviate this limitation is the use of arrays. So you could, for example, define an array of integers of a given size. So the size you can either type in as a literal, or you could use a const variable to have the size defined. Const int my count 10. Oops. And then you can define your array. You specify a type of what do you want to store in this array. Let's say we want to store integers, so int my array, and then use square brackets to specify the count. Oops. And then you will have basically reserved a memory block which contains 10 integers, and each of those integers can be then loaded into a register. You can do something with it, save it back, and then proceed to work on the next integer in your array. And of course you can initialize those. So as you know, normal variables we just initialize by providing a value. Here it's quite simple. We just use the curly brackets and then we provide the values as a comma separated list. And we need to provide as many or less values. So if we just provide a few values, it will be fine. But if we provide one value too much, it will complain. So as you see, it is complaining that it can no longer fit this value into the array. And pretty much all the modern compilers, if you provide any value, will pad the rest of the array with zeros so that you have a defined starting state. But if you don't provide anything, C++ usually is not initializing the memory. Respectively, in debug builds, it initializes to a known invalid value, which should allow you to see that something is wrong. Because in modern operating systems where memory gets cleared before it's assigned to your application, if you're doing something and are using variables which not have yet been initialized by you, they will often contain the value 0, which might in your case actually work. So the idea is that the compiler will, in debug builds, pre-populate arrays always with some garbage value. I think it's CC. So 0xCC, and then it is very likely that if your code does not initialize this to something valid, it will run into some bug, so it will find that mistake rather quickly. So let's see how we can go through such an array. Also one note, you could, as said, just write 10 here directly, or you could just, so if you are initializing an array, you could not specify the size, and then the compiler just looks up how many elements there are, and then however many elements you specify, this is the size of your array, and this size will be used. So that's that. And one important thing is that if you are using a variable, as we do here, this variable must be, well, not a variable but a constant. So if you actually turn it into a variable, then it doesn't work. The reason is that a normal variable expects to be changed, and however, the size of an array on the stack, so here inside our function, is expected. It must be known to the compile time. It cannot depend on something that might change. There are other ways how you can define arrays from a different memory pool called the heap, where you can just specify the size dynamically, and how this whole things work. We will take a look in one of the later lectures, or maybe today much later, depending on how fast we are progressing. But the general idea is that simple arrays are just defined like this, and then you can get and then you can just nicely have a variable which contains their size. However, since there are different ways to make such an array, as said, you could just not have it. One might also be interested in getting the size of an array. So if you have defined it and you don't know how big it is, you can write just int my size is equals size of. And now the not so great thing, because if you make a size of array, you can run it, you will not get 10, you will get 40, because size of gives you always the size of memory. It does not count the elements. More modern versions of the language might contain a count of macro of some sorts, which is at some point defined somewhere deep in the depths of your C runtime. But there is a very simple way to just do it by hand. You just take size of array, divide it by size of int, although that's like the very most by hand way of doing it. If you change this to a longer int, then you are already screwed, so not great. But what you can do, since size understands the asterisk and other syntax is, you can write something like this, and this already hints on how you are actually addressing individual entries in an array. You do this using this square brackets. So what we basically do here is we get size of the whole array divided by the size of the first element in the array. All the elements in a C array are always the same size. There is no case in C where you would have an array of differently sized elements. You can of course construct some custom data type which might behave like this, or you could just use a memory range and then just throw something in. But any array defined in C or C++ will be constrained to this limitation that all the entries have the exact same size, which is for the way the array works absolutely necessary, as we will see as in a second when we try to iterate through our array. So we already have some variables, so this would be good enough. So let's for example make a loop which will add all the entries in the array to each other. So just sum all of them up. So first of course, we reset one of our already defined variables. Then we use a for loop. We have already learned how those loops work. We define int e is equals 0. So that's also a thing to note in C++. Arrays, the array indices always start with 0, which as far as typical programming languages are concerned is a almost universal default. There are only a few languages which start at 1. I think MATLAB script is one of those languages which actually counts at 1, because they try to be like more mathematical, and usually the mathematicians start their things counting from 1, not from 0. But in information technology you always start at 0, since that's a convenient value, and in some way we will see why it is so convenient in a second. So we start with 0, then I must be less than size. So accessing an array at the index equal to its size would be already accessing one element too much. And then of course we'll have an I++, so that our loop does not end, so that our loop actually ends and not runs endlessly. A loop without this would in this case run forever. So we take our variable plus equals, we take our array, we address it at e, and let's put a breakpoint here and take a look how this looks. Oh, and of course we forgot to take a look here how those things looks, but this is fine, since we have already seen to some extent how those move and move pointer opcodes operate, and here you would just have a move PTR instead of a just move. So you kind of have already seen how pointers work on the machine code level, and of course here in the loop we'll again have an opportunity to see it explicitly. Okay, so we have here our for loop. We click here to step one by one. We have our check. We had our initialization, and here we are doing our incrementation. So let's see what we do. We load something into RAG, so I guess we are loading the value of this thingy. Let's see, our resetting at 2.0 was here. My value is so here we apparently load from our array already. We are not loading this, but we are loading this array from 1. Let's see what will happen when the registers when we execute this. So we have we have loaded the I. That can also be. We loaded the value of I into our register. Let's see, where is I? Yeah, that is I. So here was our I0. I lives at the address of 1A40, and here we are loading this. So actually the first opcode is to load I into the AX register. Then here we are doing a move operation. So and this we take the, and this basically will be to the loading of array into EAX. So as you see here, the opcode is has quite a few more bits and well bytes, and what it here means is basically we want to load into the EAX register. So it's basically the same register where we have now the index variable, but the value to be loaded will be the value of the RBP register, which is defined somewhere here, RBP, plus RAX. So the register can take its own value before it overwrites itself, and RAX will be multiplied with 4. So all those informations, everything is encoded in this short byte sequence, and then we can even also add to this thing an offset. Now, usually it will not like work that you can have an arbitrary value like 20 times 27 encoded here. That would be more complicated, which we can also take a look at later. But for the typical sizes, there are special bits that can be marked in the opcode to indicate that it should do the operation. So once we are done with this step, we have seen that RAX has been loaded with 1 from our array. And then RBP plus 4, that is our my variable. So then we just make this plus. So we load to a new register, ECX, then we add our 1 to it, then we, for whatever reason, copy from ECX to EAX, and then we save EAX to the memory location of our myvar. We could have here just have move ECX if the compiler would optimize it to do it, but it doesn't. So let's step by step. So alright, I didn't click widget. So we have here, then we do the incrementation, the comparison, and then we repeat. Then we load the value here. Right, so we load our I is now 1, since it's the next iteration of our loop. And now at the offset, the index of well, maybe we should have selected values which are not quite so close to our index values. They're just off by 1 basically. So let's use let's use different values. Okay, so we repeat. It was not the right thing to do. We need to here step with this thing. So we and 10 basically is A. So we see here when we go again through the whole thing. Here. So we load address. Well, so no, we load index, which is in this case 1. So it's the second go through. Then we load 20, which in hex is 14. So here we already see the hexadecimal notation. Then of course we do what we already have done before. Then we next index is where we need to load it. Next index is 2, and it's 1e, so it's this one, and so on. So as you see, this is how this works here. And again, if this would be some ARM architecture, some RISC architecture, we couldn't have such complex instructions which takes an address from this, adds this, does that, and then does even more things. So such complex instructions are something really that you nowadays will only find in the x86-64 architecture. Of course, historically there were more than one CISC architecture, but I don't think any of those are still in wide use nowadays, unless for some very legacy applications, like when you have some old system and you just want to keep it running with old code and stuff like that. Okay, so that's that. So let's see what else we can do with our arrays. One, of course, important thing to keep in mind is that we absolutely would never want to access an address here which is not valid. So we could, for example, just for the purpose of breaking it, forget to divide so that it goes until 40, and then we just run it, and it didn't even crash. The value, of course, here is complete garbage. Actually, it's not even that worse because probably most of the memory was zeros. So if we go to the address of our array, well, okay, it's not zeros, but it's the CCCs. So what happens here is that even though, so first of all, we should demonstrate that we are really accessing invalid memory. So let's put a breakpoint here. Then just turn the hex off. We have here our index, and I just press F5 to jump to the next loop iteration and next breakpoint. And basically, we here see we really are now accessing indices which just don't exist, and the computer is executing this completely fine. It doesn't even crash. At some point, if you would like say that, let's go to some really large number, it will end up in a crash. So we can also demonstrate this. And bam, we have an access violation. But this only happened because we looped so far into not yet defined memory that we have reached a memory address which for this process has not yet been so the addresses basically start at 0 and go until 8Fs if it's a 64-bit system, but of course you don't have some 16 exabyte of memory. You have a few gigabyte, a few 100 gigabyte, maybe you have a few terabyte if you are particularly wealthy. Nowadays the RAM is quite expensive, but obviously you have much less memory than memory addresses, and basically the operating system, what it is doing is it's assigning through so-called memory page translation tables, usually 4 kilobit, in some more modern systems 16 kilobit large chunks of memory in your physical memory towards addresses inside of your virtual memory space in your application. We will be discussing this in more detail once we take a look on memory management. It will be one of the upcoming lectures. Then we will explain what the stack and the heap actually is. But enough to say that you can access any memory that is valid, and as soon as you try to access an address which does not map to memory which exists, then the application will hard crash. And this behavior that you can read or write any memory within certain restrictions, so you could of course set some memory pages to be read-only, then you cannot write to them, you can only read from them, but since the memory doesn't have any other properties but readable, writable, executable, etc., and this only in a quite coarse granularity of, as mentioned, 4 or 16 kilobyte, this means that your program, a C++ program, which is so closely implemented to the hardware with any additional checks, just doesn't have any means, any mechanism how it could validate that I being 10 or being 20 or something is no longer a valid address for this array. It just tries to read memory. It really just does what we have seen in the opcode. It takes some base register, it adds some offset, it multiplies, it adds the index, sometimes multiply it with some value, and then it just tries to read or write to this address. So if we would be writing to an array, we could actually cause some memory corruption. We could overwrite some other parts of memory which we didn't actually intend to overwrite. And this is quite a problematic thing. So we could here demonstrate this. I will set up a test case later to demonstrate it, but for now let's continue just with the important things about this array. So as said, the array will not prevent you from doing something invalid. So as with many things in C and C++, you have to think about what you are doing and not rely on the compiler holding your hand and helping you on the way. It's very easy to write something that looks correct and then just often maybe even works, and then in some case breaks in some very weird way. thus, of course, in modern C++ style, you would try to not use a just a C array, for example. You would use more modern mechanisms, which we'll be discussing during this lecture. But those mechanisms are basically just wrappers around this basic primitives, which we are now here learning as part of the just C part of the course. So the next thing I think that is interesting is how we would handle if you would want to have a pointer on an array. And as a matter of fact, an array and a pointer semantically in C or C++ behave quite identically. So if we want to have a pointer, so if we want to modify our array using a pointer, we'll just have a int asterisks my ptr, my array ptr is equals, and then we just write the array. So an array just as a variable usually can be just treated as a pointer. Thus follows that a pointer can also be treated as an array. So if we assign this here, we can just use our pointer and then address it with I, and it will work the same way. The code will be slightly more convoluted because we have one more level of indirection, but from a semantic standpoint it does the same. What doesn't work, of course, is to try to use size of. If you use size of on a pointer, you can get the size of the pointer, or you can get the size of one element the pointer can point to, but you cannot figure out by principle how many elements are in the array the pointer is pointing to. With the array, as said, this works because the compiler knows this and it can fill in this value, but this information is only existing in your source code. It is not in any sense persisted into the compiled output. The compiled output, well, implicitly it might be in some places, of course, if you have some variables which then are supposed to contain it, then it will be, but it's not a property of the array in memory as it exists, how large it is. And this is a very dangerous limitation of C arrays that is responsible for a great amount of bugs that are quite security sensitive. So let's take a look here. We can also try to compare the code with the previous code. So the previous code had like, we load an address, we load the value from the address, and then we start doing things. And here it is, when you look at it, it's one move more. So it's actually quite not that much more complicated. But it is still a little bit more. So what we do here is we load RBP plus 1 plus this. So this will be, so first we of course load our I as we did always, since we wanted to do something with it, and then here we load next thing, and the next thing is the address of our pointer. So basically what we want then to contain here is, we want to get the value of our pointer, so what the pointer is pointing to. That will be then stored in the so this RBP plus something is the address of our pointer, and we are reading the value from world point to into RCX. So RCX will be then the address of our array. You can step. So now RCX, we can go to memory, RCX, and then it contains so A is 10, 14 is 21, and so on. And then we just use here in the next line this RCX register plus rax times 4. So rax is a copy of our I. So it's quite similar to this, just that it adds. So we cannot here directly like we cannot like dwort ptr from another dwort ptr. We can this operation here plus this. So the order is a little bit not so ordered. Basically, we have RBP plus this, and this is already the position of our array. While here we have RBP plus something different, which is the pointer, the position of our pointer, from which we then take the value, which will then evaluate to basically effectively this RBP plus this offset, which then will be stored in RCX, and then here we just add RCX plus RAX times 4. Here, as you see, the opcode is already quite a bit shorter because it does not contain any sort of additional offset. It just contains registers and encodes the semantics how those registers should be combined to each other to generate the right final address. And then the rest of the operation is quite identical. We are where was it? Here, although it's not quite as identical because of course, wait till we will write back. No. We are not modifying our array. That should be identical. Let's see. So we have move. So we have move, add, move, and here we have move, add, move. Yeah, we have the same code as expected. So basically this adds one additional instruction, but this is not something that would be particularly detrimental for the performance. So let's see what else we can do with pointers. So since we know a pointer to a single int or a pointer to an array of ints is still the same pointer basically, there are a few things we can do with pointers, and since we know that they are just a number, we can of course do mathematical operations with those numbers. So if we have our pointer here, then we could, for example, just increment it by 4, and then it would no longer point to 10, but it would start pointing to 20. Of course, if the loop would keep running, then we would then be pointing to something behind it which is not valid. But in fact, such pointer arithmetics is a very common thing done in C and C++. Again, it's a bit risky, but it's also very convenient. So what we would want, for example, is already have our variable here. So let's make another loop. We will skip initializing anything first, so we just leave this empty. We can add a space for it to look nicer, and then we will have our address, and the address should the condition for address will be basically as long as the address is less than array plus array size. Yeah, as long as it's smaller, it's valid. And then here, of course, we would we want to do this in a different way. So here we would just take a value at the address of the pointer. So basically, this is equivalent to 0. So whenever you have some pointer or array from 0, you could also just write asterisk in front of it, and vice versa. But depending on what you are doing, the code is more readable if you keep those a bit separated. So whenever you are just dereferencing at a given position, you just use asterisk, and then if you are really addressing an array, usually not with constant values, then you are using this static way of doing things. So the question is, of course, how do we advance to the next element? Because as it is now, this would be again an endless loop, and this is quite trivial. We just take our pointer and plus it. And the important thing about pointers, since they have a type, since the compiler knows which type this pointer is, this plus operation will not be like +1, but will be equivalent to and now this one must be careful how to write. So because any mathematical operation like plus or minus on a pointer will work not in increments of 1, like, well, a normal mathematical operation would, but it will work in multiples of the pointer size. So if the pointer would be a char, then of course it's 1. But if a pointer is like we have here an integer, then it's always 4. So basically this plus so So technically, if you really would want to properly write this as C code, we just say that this plus plus is equals. We cast the pointer to an integer, and then we make plus 4. So if we this was also wrong. So if we cast a pointer to an int, then it will behave like an int. Then it's just an int number, and the int number, if we plus 4, then it will be plus 4. While and this thing plus 4 would be effectively a plus 16. Right, and this way we will then end up again going through the whole array and adding all its values to each other, like we did before. Any questions so far? Okay, if there are no questions, then let's continue. Yeah. Anything else that's worth mentioning? Yes, since, as I said here, those things behave kind of similarly, you could also, this would also be equivalent to plus e, and then asterisk. So this code and this code is exactly identical. It does exactly the same thing. You could also do it here, or we can go with a more fancy version here. We could have a int asterisk my tmp array, or my tmp I'll just call it my temp is equals my pointer plus I, and then in the next line you could then asterisk temp, and what we now of course could do to make this even more fancy is to cast this to int plus I times size of int, and then we need to cast this back to a int asterisk. So usually these casting operations are telling the compiler how to interpret a certain variable. In some cases they invoke a actual conversion. For example, if you have if you are working with floating point numbers, even if you cast, then it will actually properly convert it. It will not just reinterpret the memory, which is why we needed this trick with the pointer, because a pointer is always a pointer, and if you cast only the pointer type, it will really only change the interpretation of the variable. It will never trigger an actual conversion of the values. So here what we do is we convert, oh, and this is obviously invalid. We need to use a data type which is large enough. This was here also a bug. So if we would cast a pointer just to an integer, then we would end up with truncating some of the address bits and then with an invalid address. So of course we need to ensure that we are using the right type. So int64 would be for a 64-bit platform. So then we have our int, then we can increment it by adding I times size of, and then again we tell the compiler that this address, or rather this integer value, is now to be treated like a pointer to an int asterisk, which then can be dereferenced such that we can obtain here our value. Okay, so let's continue. As I said before, we can also write to arrays. So let's make let's just copy this piece of code and assign our array some new values. So array from I is equals, let's say, I. So if we just do this, then we will end up with our array just containing the new values. Although we wanted, now it's like setting at 0, we could also make like I plus 1 or whatever we want. But now what we should do is we should define a second array. let's just initialize it to 0. Here we have our code still running correctly. So we have our two arrays. And then let's see what happens if we, let's say, tell it to go to 20. Now, of course, what will really happen will depend on how the compiler will align memory. For example, we see here, so we had this array should always be 0 because it's defined to 0, and as far as the code is concerned, at least as far as we see it on the first glance, it is never being overwritten. But since we run here our loop for 20 iterations instead of 10, so we reached the end of this array and then we just kept going, we managed to reach the memory of this array here. And the interesting thing is that there seems to be some memory gap, so there is some memory in between which has not been used. Like 6 bytes are unused, and then we started overwriting this array with the next values here from our loop. And the reason why there are 6 bytes unused is that usually nowadays compilers try to align memory accesses to optimize performance, and they do it in increments of at either 42 or 64 or 128-bit. And here, since our array is basically one 64-bit block plus 16 bytes, it leaves a part of the block unused, and then the next array starts again at a clean 64-bit boundary. This memory alignment mechanism we will take a look on in one of the later lectures as well. It is important to know here that however, that such bugs, as we have seen here, are quite difficult to catch, because as we have seen, the compiler neither in compile time nor at runtime really told us that here some memory corruption might occur, and depending of course on what gets overwritten, the result might be very catastrophic. So a lot of exploits in the past were based on just overwriting some buffer with executable code, and at some point if you're writing long enough, you would reach an address which already contains executable code, and then if this code then ever gets executed, since it got corrupted, your code will be executed instead. Nowadays, this particular attack vector has been mitigated in hardware, so nowadays memory pages can be marked as executable and read-only, or you can also do the opposite. You can mark memory pages as non-executable. So this allows so ideally a modernly compiled application should have only memory which is either executable or writable, but no memory which is executable and writable at the same time. There are some cases where this is not convenient. So if you, for example, have for example, a JavaScript interpreter, it would often try to interpret the JavaScript into machine code, which then can be executed. So whenever you have some on-the-fly dynamic code generation, there are still risks of having memory corrupted. Although the correct practice is that you set the memory writable but not executable. You fill it with whatever you want, and then you switch it to be executable, so that at no point in time it is both. But this is of course something for later. We will take a look into this when we take a look on memory management in more detail. Okay, let's see what else we can do with pointers. So as you've seen, in case of this floating point number, of course, we can use such pointers to address data more directly. But what we can also do here as a demonstration, let's write another integer, or let's reuse one of our integers. Zack, let's fill it with values. Is equals 0x 1 2 3 4 5 6 7 8, and then let's define an array of characters, my chars. And what we can now do is we could, for example, do the same trick, char asterisk address on this, and then we'll be able to get the individual characters out of our array. So char1 is equals, let's 0, oops, 1, 2, 3, char 2, 3, 4, and let's put a breakpoint and run. So X display again. Again, we can then get out our variables quite nicely. Yeah, and we also can notice here, I'm not sure if I mentioned that in the one of the first lectures, that while a number like starts most significant digits towards least significant digits when stored in memory, the order bytewise is reversed. So the first byte where the pointer points to will be actually the least significant digits, just those two here, then next two and so on, and only the highest one will be the highest significant bits. And one reason why this is quite convenient is that if you want to convert, let's say, to a number that is not quite as long, to have just such a number, so we would have the higher order bits would be zeros, 0 and 0, and here you have your two numbers. Then if you are casting, so to have, for example, a short, oops, then it just memory copies at this address and the value stays intact. You might lose, of course, the higher order bits, but ideally you would have some check that checks whether you would actually run into such a problem or not. It is usually not recommended to do such things without really checking that the value range will be acceptable. So one case where you would, for example, do such things is when you have your pointers, they of course are only valid in the context of the current memory layout of your application. So if you want to send some more complex structured information over the network or save them to a file, you cannot transmit a pointer to the other side or to another instance, because it will be simply invalid. But what you could do instead is you can transmit an offset. So you say you have a block of memory, you transmit the block, and the block at defined place would have offsets, would tell at this particular offset inside the block there you can expect this or those data. And for such things, what one would usually want is you would not necessarily want those offsets to be 64-bit, because probably your data will never be as big as 4 gigabytes. So there you would truncate your offsets to only 32 bits. But you would start out with the full computation. So let's make an example. Int my offset is equals, so we have our array. Let's also right here. So int my 1 will be, let's say, we want that to be in the pointer, my r1 my r item 1, like this. We can either +1, or we could use let's say 5, the other notation 5, but then we need to take its address. So in both cases we are basically getting just some individual just a pointer to one item in the array, and then to compute our offset, what we would do is we know those are numerically always higher than the actual array itself. So we would have this value minus array. Although, as mentioned before, one has to be careful, because this will, as written here, not do the right thing. or rather it will depend what we define as the wait, there's another bug. It will depend on what we define as the right thing, because here it will give us the numbers. Well, there should be 5. It will give us sorry, it will give us the numbers 1 and 5. Sometimes when I'm talking too fast, my tongue gets entangled in itself. So if I'm talking too fast, by the way, just tell me to slow down, because I'm notoriously known for sometimes talking too fast. So I said we get here these values 1 and 5, because the compiler here treats this as a pointer arithmetics. And if you would want to use offsets inside the file or inside some blob we send over the network, we might not want the offsets to be contingent on the knowledge in which increment they are. So what we would want would be to have the offset as bytes and not items. So one way, of course, would be to just multiply this with size of my array at 0. That would give us already here the right offset. And the other option, of course, is to just cast this to a char asterisk, both of them. Of course, now as soon as only one is cast, it complains because now the types are incompatible. And then it will work in the same offset. So when we run it now, we will get 4 and 20, which is in hex notation 13. So, and this offset here, now in this case the compiler might complain depending on our configuration. Let's just build it without running it. And let's see, so we already get some warnings here and there. So in fact, each of them generates kind of a warning of its own, but both are saying that there is a possible data loss, because these things here, in both cases, even though formally they will be different types. So when you do true pointer arithmetics, you would get something of the type size t, which is just a placeholder for an unsigned int64. But the idea with the size t is that on a 64-bit system, size t is 64-bit. On a 32-bit system, size t is 32-bit. And on an Arduino, it is probably 16-bit or whatever the current Arduino is using. There are also 32-bit Arduinos nowadays. So the nice thing of this size t is that it always adapts to whatever you are compiling your project for right now. And of course, if we cast this to chars and then work just on the direct values, then we get this result. Also, another thing we could do here is if we cast this to a int64, that will also give us the same value. And then it's definitely no longer any sort of pointer arithmetics. But as said, the compiler is complaining because it does not know that the values will always be within a smaller range. So what you would usually do in such a case is you would just explicitly cast it to an int. And if you do a casting to a shorter type, okay, that was not a great demonstration. We want to just build it. So if you are casting to a shorter type, the compiler takes this as a hint that you know what you are doing, which also means you should not be putting you should not be casting things when it's not necessary, because then if you change something, that might hide a potential warning. So you should only do casting if you need it. For example, if either the types are incompatible such that it would not compile at all, or if you have a warning that you want to suppress. And then of course, once you have such offsets, you can easily generate some. So at the other end, we would have let's take some pointer. Let's reuse our array pointers. So you would have some array pointer which is equals your initial thingy, and then if you want to get back those two addresses, you would, we already have defined them, you would just take your pointer and add to it your offset. But here, since it's in bytes, it would again not be correct, so we need to cast this to let's first go with char asterisk plus this, but this again here doesn't assign because now it's just a number, so it needs to now know that it's not longer a number, that it's a type. And here the other way of doing it, let's copy it, not type too much, would be to use int64, and then it would also work. What you could also of course do, if you want, you could go with this thing times offset times well, size of int. Let's go with that. Wait, is that correct? No, it's not correct. That needs to be divided in this case. Yeah, now it should be right. Let's see if it's right. So this contains a pointer to 1 and this contains a pointer to 5. So it still contains a pointer to 1. Ah yes, because I did not change this here. Should have been 5. Yeah. And generally, if you are working with offsets, it is very customary to really use the byte offsets because this is much more fail-safe in a way than assuming certain size. So to give an explicit example, if you would have used an array of size t's, then this size t, as already mentioned, would change its size depending on which platform we are compiling it. So for example, if you compile in both cases for Windows, but once as a 64-bit application, once as a 32-bit application, then you would already run in such a problem. Okay, any questions? Okay, so if there are no questions, then we have 15 minutes left. So we could actually take a look into something quite conveniently simple that I think should fit into a 50 minutes time frame. That would be this preprocessor I mentioned at some point during this lecture already. So for this we'll create a new project. Zack. Not working. Zack. Create new project. Next, preprocessor, create. So the idea of how a preprocessor works is really quite simple. It kind of allows you to define rules how your source code file should be edited by the preprocessor in a step before it gets fed to the actual compiler for compiling. So one thing you can do is you can use a define and then define some def my define, and you can just either define it that this thing exists or you can give it a value. And then if you have int my var, you can, if this thing has a value, assign it. And the nice thing is that this really works like a search and replace sort of operation. So let's call my var1. Let's have my var2 is equals 1 to 3. Oops, 1 to 3. And let's then make another thing and variable 3. And those search and replace sort of operations, they can be quite non-trivial. So you can make a thing that in some way takes arguments and allows you to my add, let's call it a comma b. So you can specify two names, and then you can write some, this should not be complaining, and then you can specify what happens. For example, you could say that it should do a plus b, as trivial as it gets. And then here you just write this is equals add def my add var1 comma var2 semicolon. And what it really will do is it will turn this line explicitly into this line before it compiles it, before it really compiles it. So it's really quite quite a funny mechanism, and it can really be used for quite complex things even, since you could, for example, make another sort of add 2, which takes a, b, and c. Then you could say that this thing should evaluate to a equals b plus c. Need to the comma. I need to not forget the comma. And then you could, instead of doing like this, you could just write add 2. So this comma those two, and this will then end up, even with those curly brackets, zack being this. And what you can also of course do is you can at least in C++, a comma no, b comma c, do something like that. So you can even refer to other defines in your defines in C, in just C. So if you have a file that has the ending C, not CPP, this is only partially possible. So there are quite significant restrictions. But in normal C++, you can make quite complicated things. So what you of course could also do is you could even use this to define variables. So for example, hash define def my def int x and int x, and then you just define my var 4. Wait, if there is a semicolon here, then I don't need a semicolon there, and need it here, my def int. This does not need, so it's quite, you cannot have a white space here. This needs to be free of white spaces, which is unlike other things in C++. So for example here, it already is fine if there is a white space, but in the definition there must be none. Right, and then you can just something. So in this case it even broke the indentation, but since we have a semicolon here, we didn't even need this here. I would only add this one here for the purpose of this not getting always indented when I edit something. And another thing you can do with those defines is you can use it to enable or disable code blocks. So for example, hash if def if def so if def this, or actually if def this, then use it hash and if and if I would comment this out, then this code block automatically gets disabled. And of course I could do it in a more complex way, like I could use a different variable for that and so on. I could have also like an else, hash else, in which case, okay, so actually this we can always have, but here we would need to int x. So if we have our special define macro, then it, well, not x obviously, then we use it, and if we don't have it, we use the other code block. And you can also have like an define int def short. So if def int, then int then short, well, short of course. Short, then use short. So if we have both, it uses the int, as it falls back to short, and as it falls back, let's keep this as small as possible. Let's go char. So you can do quite many nice funny things with this preprocessor mechanism. And one thing you can also do is you can take a whole other file and then basically copy paste it into your file. So let's call it header1 h, and so we have here the header, and we can take those things here, put them here. Now obviously the thing is complaining because it doesn't find them anymore, so we just include header1, and voila, it's as if the whole code from header1 would have been exactly here. And of course there is a catch-22. If we add another header, item header2, oops, h, and now let's split those thingies. So let's leave the adds here and put those things here. By the way, you might notice the compiler created this pragma once. Let's disable this. Okay, so we save both, but here we kind of maybe want to have header1, so include oops, 1h, and now we are here, so we have header1, but none of this is included, so we now include header2, and now everything is included. So the one file takes the header1, pastes it into itself, and then when it's included, you take the whole resulting thing and paste it again here. And in fact, in some compilers you can set it up such that you will get those intermediate files generated for you. But I think on modern compilers this is not longer possible that easily. And of course, one situation where you might run into is if you include header1 and then you include header2. Oops. Now it actually looks fine, but if you try to run it, it should not be happy. It might actually wait. It depends on what's contained in your header. In this case, it will just issue a warning. It should issue a warning. Did we disable this? The one header2. Normally, that should issue a warning that some of those things are already defined, since we have basically included header1 twice, but apparently it doesn't want to give us the warning. We can maybe try to do it differently to trigger that. Let's see, it doesn't work. So generally, if the compiler is not too smart, it will, if it sees that the header is included twice, just include it twice, and then it will complain that with a warning like this that something is already defined. Then let's define it something else. Maybe it's fine because everything is the same. Okay, now we can run it to a redefinition. So the preprocessor macros are not a good example. If they are redefined to the exact same thing, then it doesn't trigger an error. But generally speaking, if you would have two headers and one includes the other header, then you might run into warnings or errors because this code exists kind of twice. And this pragma once is a preprocessor macro which tells the compiler to be intelligent about it, and if it sees a header already has been included, then it omits the appropriate include directive. And the way how this has been done in the past was also using preprocessor define. So just have defined underscore header1, for example, and then you had if and def header1 and if hash. And this effectively meant that if you have already this way, yeah, that makes sense. So if you include the header for the first time, header1 is not defined, so you do the thing and you define your header1, and then if your header1 is then included a second time, after it has been already included by something else, like here, then it sees that header1 exists, and then it keeps doing everything. And this mechanism in modern C++ is basically just replaced with this pragma once, which is quite convenient. Okay, what else can I tell you about the preprocessor? So there are a few more exotic use cases. So um, let's improve our define variable. So my hash x. Okay, so the idea is that this allows you to concatenate even in names. So in this case, if we go back here, this of course is wrong because here we still have like my. If I would only pass 4 here through the thing, then this should although that might actually not work with that's so that should be var4. No, it's fine. So basically what you do is it takes just this string, concatenates it here, and if you would just have my x, that wouldn't work because my x might be an own thing. It really needs these 2 hashes to tell the preprocessor that it should actually do this string concatenation. Another nice thing is that you have already quite a few such defines predefined. Normally you can set them here, preprocessor, and as you see here, we have, oops, that was not intended, abbrechen. Properties, zack, edit. You have some that are really defined in the project here, like debug and console, and then you have also one inherited called a Unicode. And on modern on Windows systems, you would often also have a Win32 definition, like here. So you can then use this to differentiate the behavior of your application depending on for which project you are building. The most important is somehow a bug with right-clicking in this new Visual Studio is between release and debug. So the release build has like n debug, while debug has underscore debug. So when you compile your application, you could write some hash if def underscore debug hash end if, and then you can write here code which will only be executed if you build a debug build. If you go to a release build, the code will be automatically disabled. So for example, if you expect that certain error state should never happen, then you might not necessarily check for them in the release build, but in the debug build, since you want to ensure that you will find the bug if you have a bug, then you can add additional checks which will probably slow down your application but make it more safe. And this can be done with this debug macro. There are other definitions which are also available, like for example hash define underscore m underscore x64 hash and if which is we don't make it complaining if def. So this thing in fact is defined automatically, even though it's not there in this list. So some additional macros are added, and also some macros are available in headers which you might include. So you can have quite many of those. And this mx64, for example, tells your code whether it is a 64, an Intel, well, not Intel, an AMD 64, or a Intel 32-bit code. So you can add even more differentiation like this. In principle, you could also use a simple mathematical expression. So if you have defined this as 1, 2, 3, you could have like, but just not if def, just if my define is greater equals 1, 2, 3, then hash and if. Yes, and if you make it greater equals 4, then it will be no. So you can be quite flexible. So for example, you could have like a version number of a library that you can then check for and then bug out if something is not as you want. And you can even make more complex expressions. So you could, for example, hash if I see we are running out of time, so I'll just finish this example and then we'll finish for today. not defined MS64 and not defined underscore m underscore x64. Do I have enough brackets? No, it's enough brackets. Hash and if. Then we could. There is a nice precursor macro called error, which will just cause your compiler to throw an error. Sorry, this code requires a 64-bit CPU. So if not, is this correct? No. If not this and not this, that was right. And if we switch to a 32-bit CPU, it will bug out. But if we would have add a profile here for ARM, it would also be happy. So yeah, that's it. And of course, maybe one last thing, since as mentioned, this include statement is really just a copy and paste. We could have a we could have really like include just some or it's just some anything. Add new item or add here. Let's say int my hidden variable like 1 to 3, and then here we can include this. Let's complaining. I mistype something. It should be fine. Rename. I just copied. Yeah, I had some I had the typo somewhere. I didn't copy my hidden variable. My hidden variable is equals, and this also works. So we really could like take any portion of your C++ file or your C file, put it in some other file, and then just include it. Not the most readable architecture, but there are some cases where this is useful as a trick to know and to have in your bag of tricks. Okay, and I think this completes our small detour into the preprocessor. If you have any questions, you can ask me during the next lecture. There are much more different built-in defines, like not this, for example, this one that gives you the current line number or the current file name, stuff like that. Particularly useful if you want to put this in some warning messages, etc. Okay, so I will upload the 3 projects to Moodle and the homework assignment and of course the recording, and we will see each other. Oh, I think not next week, because next week there are already holidays. Where is my Thunderbird? I think we will see each other in in 3 weeks from now, since there are 2 weeks for Oster holidays. So we will have more than enough time to do the homework. And if you have any questions in the meantime, you can write me also during the holidays. I always read my emails. So have a nice holidays and see you later. Bye bye.